everyone, welcome back, and today let's solve Leetcode problem 342 titled Power of 4. So we're given an integer n and we need to return true if it is a power of 4 and else return false. And we're also given that definition of an integer being a power of 4 if there exists an integer x such that 4 to the power of x gives that integer n, as you all probably already likely know. So something like 16, 4, or 64 would all be powers of 4 because 4 to the power of some integer gives these values. However, something like 8, 12, or even 20 would not be powers of 4, although they would be multiples of 4, because although 4 times some integer equals these values, 4 to the power of no integers gives you these values. And so these wouldn't be powers of 4, but rather only multiples of 4. So in example 1, we have our input integer n to be 16. Why is it true? Well, because 4 to the power of 2 is indeed 16. It is indeed a power of 4, and so it is a valid true output. In example 2, n equals 5 isn't even a power of 2, and hence it cannot be a power of 4, which is also a very important insight to make in the future. And so we will return false. And n equals 1 is kind of a special case where anything to the power of 0 is still 1, so 1 is technically an answer to the power of anything, and so this is still true, right? So that kind of brings us to the main insight that we really need to make here, in the sense that, okay, well, if something is a power of 4, it has to be a power of 2 as well. Why? Because 4 is a multiple of 2. It really just is 2 squared. And so if something is a power of 2, like 4, 16, 32, and so on and so forth, only then can they even possibly be a power of 4. If something isn't even a power of 2, like something like 5, 7, 9, or 11, or 13, any odd numbers, they have zero chance of being powers of 4, because they have to at least be a power of 2 to even have any chance of being a power of 4, because 4 is a multiple of 2, right? Which brings us to that main kind of efficient approach. Now, the follow-up kind of asks us, can we solve it without loops or recursion in the most efficient time possible? Because our constraints are indeed 2 to the power of 31, which is the largest possible, and so we can't actually have anything worse than a big O of 1 solution. So something like the standard solution of while n modded by 4 is 0, meaning while n is divisible by 4, you could divide n by 4 and return if you eventually get 1, because for all powers of 4, you could always be able to divide them by 4 until you get 1, until you get that 4 divided by 4 equals 1 loop, but that would be too slow. Why? Because we have too large of constraints, which is why we have to follow it with the follow-up without using loops or recursion in the most efficient way possible. And that brings us to the most efficient way, leveraging the fact that, okay, we do need to make sure that it is first a power of 2 and then check if it's a power of 4 using the bit and actual bit values in the actual bitwise representation of our input integer n, right? So what is the most efficient solution for this problem here? It is going to basically just be bit manipulation. Again, because we know that powers of 2 always have exactly one bit that's set in binary, right? For something like 1, the binary representation would be 0, 0, 0, 1. For 4, it would be 0, 1, 0, 0. And for 16, it would be 1, 0, 0, 0, 0. It's always going to have exactly one set bit. And we know that powers of 4 that have a single bit are always going to have, or rather, sorry about that. What I meant to say is powers of 4, right, as we discussed, is the second check that we have to kind of do, right? And we know that powers of 4 that have a single bit is always going to be in an odd numbered position. And that's going to start from position 1 for the least significant bit, right? Why do we have to check that? Well, because first of all, if we know that our input n, if it's actually a power of 2, so if n is a power of 2, only then do we check, okay, is n a power of 4. And we do this by leveraging the fact that we know that powers of 4 that have a single bit are always going to be in an odd numbered position. And when I say single bit, I really mean single 1 bit, if you will, like we saw for 2 as well. For a power of 2, it just has to have any single 1 bit. For 4, that single 1 bit has to be in an odd numbered position that starts from position 1 for the least significant power, or rather the least significant bit, if you will, right? So that actually brings us to the main coding solution here. It really is a very simple kind of solution, if you will, really only 3 lines, and I'll kind of break it down. You can really simplify it to really only 2, but just for kind of simple explanation, I'll make it 3. So the first case that we're going to check is n even positive? So if n is less than or equal to 0, if it's negative, or if it's 0, we immediately return false. Why? Because 4 to the power of any integer x is never going to give you a value that's less than 0 or equal to 0 by that means. So if n is 0 or it is negative, we immediately return false, right? Because it cannot be a power of 2 regardless of anything, really. I think my indentation's a little funky here. Let me just redo that line of code. Okay, so that's the first quick case kind of out of the way. That's a simpler way. The next one is we now have to check, is our input n, is it actually a power of 2? That's the first check. Before we even check if it's a power of 4, we all want to check the easier case of, is it actually a power of 2? And to do that, we again use that, we rather leverage that bit set of, okay, well, powers of 2 have to have exactly one set bit. And so if n, bitwise ANDed is what I'll call this, that's the symbol or operator for that, of n minus 1, if that's not equal to 0, we have to again immediately return false, because that would mean that it is not a power of 2. Why is that? Well, because we know that if it's a power of 2, it has only one bit that's set. And n ANDed by n minus 1, if that's equal to 0, that ensures that it is actually a power of 2, right? And the reason why is because for bitwise AND operations, it basically checks if the bits in every single corresponding position is common or not, and it will give you a 0 or 1 for that specific value. And so if it's 0, we know it's good. If it's not 0, that means it has conflicting bits and digits, and that means it's not actually a power of 2. So if we've covered that it is a power of 2, we now have to check if it's actually a power of 4, and we're going to do that by checking if the bit is in the correct position for the power of 4, all right? And there is actually something called 0x and then a bunch of 5s. That is going to be 0, 1, 0, 1, 0, 1, 0, 1, and so on and so forth in binary. And that's basically just going to mask only the bits at odd positions, like the first, third, fifth, and so on and so forth positions, to be able to check if we actually do have the correct position bit, to see if it then is a power of 4, right? So the way we would do that is we would return n bitwise ANDed, if you will, by that value. I don't exactly remember how many values are there. If I remember correctly, it was like 8. I'll try 8 for now. 1, 2, 3, 4, 5, 6, 7, 8. It may very well be 9 for all I know, but we'll try that for now. And as long as that's equal to 0, we're fine. And so we really just have to check if n ANDed by this hexadecimal value, if it is actually equal to 0, right? Or this binary representation, if you will. We just have to return if it is not equal to 0, or if it is, right? So if it's not equal to 0, we're good. It is a power of 4, and we can just return true. Otherwise, we'd return false if it is. And so unless I made any syntax errors here or forgot a 5, this should be accepted, and this should be a valid solution. And as you can see, this really is just about as efficient as you can get it to be. So again, just to kind of summarize how we really solve this problem, effectively we automatically know that negative numbers or 0 cannot be powers of 4 regardless of what they are, because that just breaks the law of powers. And we also know that if n is a power of 2, it's going to have exactly one bit that's set in binary. So something like 16, to kind of just provide a very quick example, would be something like 1 and then 4 zeros in the binary representation. And 16 ANDed by 15, which is 16 minus 1, is indeed going to give you 0. Why is it going to give you 0? Well, because the bitwise representation of 15 is 0, 1, 1, 1, 1. And notice how 1, 0, 0, 0, 0, 0, and 0, 1, 1, 1, 1 all have conflicting or different bits for every bit position. And the last 4 bits or indices, if you will, these are all zeros, these are all ones, and in this one, this is 1 and this is 0. This is a very nice way to check if something has a power of 2, because we know that for a power of 2, there's only 2 options for each bit, either 0 or 1. And so if it does give you a value of 0 for n minus 1, we know that n is a power of 2, right? So if n is indeed a power of 2 and we hadn't returned false by then, we know it is a power of 2. And then we have to check in our last conditional, or our last kind of case, if you will, if it is a power of 4. And this hexadecimal number, or representation 0, x, and then I think that's 8 fives, that is actually a 32-bit mask, where represented in binary, it would be 0 1 0 1 0 1 0 1, of course 32 times, or 16 pairs of them. That would ensure that the set bit is indeed in the correct position to be a power of 4, meaning it is actually at an odd position, because only then can it actually be a power of 4. Right, so for the runtime complexity here, as we discussed while talking about the follow-up, it is actually constant or big O of 1, and the same applies for the memory complexity as well. Why is that? Well, because really we're just doing bitwise operations. We're not actually using any extra auxiliary memory or anything like that that scales linearly with our input, right? Since we do have these constants as our parameters here, and so this is a big O of 1, or constant time, both runtime and memory or space solution. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye bye.